Okay, everyone. Let's start. So let me introduce our speaker, Professor Russell Dupuis. I hope I didn't.
That's good.
Your
That's
last
good.
Name pronunciation. So we have eminent scholar from close by Georgia Tech. So he has his PhD from Illinois under Nick Illuminating, and some of you may know he. Illuminating is known as the inventor of the AD. He then went to Texas Instruments and then joined Rockwell and moved to Bell Labs, AT&T Bell Labs in 1979, and went to University of Texas at Austin as a chair professor in 1989. Then came to Georgia Tech in 2003, and he has a chair at Tech and also the Georgia Research Alliance Eminent Scholar. So he has been at most of the well-known places around doing devices, semiconductors, and he's going to talk to us about devices and what he's doing at Georgia Tech. Thanks.
Thank you. Thank you. It's nice being here. It's good to see a nice full audience here. I appreciate your taking time to come and see what I have to say. I want to especially encourage all the students here to work hard on their theses, because I have a group of students in my lab that I hope are working hard today, but who knows what they're doing. As you all know, the semiconductor industry has exploded since the invention of the transistor in 1947, although it wasn't always obvious. When my PhD advisor was in your shoes starting graduate work at Illinois, that was around 1953 or so. Bardeen had come to Illinois about that time from Bell Labs, and everything in the curriculum in electrical engineering was based on vacuum tubes. So if you were doing electronics, you were doing vacuum tubes. And when Nick made the transition to work in Bardeen's lab, he was Bardeen's first graduate student, a lot of his friends thought he was crazy. That why would you give up a perfectly good career in vacuum tubes to go to some probably, ridiculous little cat's whisker transistor thing that didn't look like it was going to amount to much because it would never be manufacturable. Clearly, that was the wrong answer. Don't stay in vacuum tubes. So keep your eye on the field you're in, and sometimes you make rather large jumps like Nick did from a well-known area to something radically new that could end up maybe not going anywhere. But if you're clever, you can always find a way to put your knowledge to good use, I'm sure. I'm going to talk about a different technology than silicon uses. It's a metalorganic vapor phase epitaxy. Some of you may know that virtually all of the silicon devices you are ever going to see, they're not bulk silicon wafers anymore. They're something much more special, and they all rely on some form of vapor phase epitaxy. So this is different in the sense that we're trying to grow 3,5 compound semiconductors. You're all familiar with the periodic table. So gallium, aluminum, indium, typically column 3, form the magic 4 covalent electron sharing on average that leads us to semiconductors in many cases. So I'm going to start with some of the historical development of this technology. Like most technologies, it started in someone's head who wanted to solve a problem with the current technology. And so I'll try to describe that and how it exploded from the kind of work that you would do almost in your kitchen or your garage to the latest technology, which is literally across the world, literally producing every device you want to buy today or tomorrow. And in particular, I'm going to talk how it applies to what I call illumination, but generally illumination, not just lighting, but information. Information illuminates the world, illuminates your mind, and also how it illuminates things we don't yet understand, exploration of space in particular. You're all with telecommunications, you use it every day. You probably are Googling your friends right now, seeing what they're up to on Facebook, assuming you don't care that all your secrets are being sold somewhere. But also it powers a lot of other things besides high-speed electronics and optical communications and the internet. It powers solar power systems, which we all use in some respect because we all are interested in space communications, in satellites, in what's happening on the space station, perhaps what's happening on Mars. Visible LEDs you're all really familiar with, I'm sure. Probably every one of you has purchased LED light bulbs. They obviously are not for free yet, but they're almost for free per lumen of watt at least. And the other aspect of this that a lot of people aren't really familiar with, I'm going to talk a little about, is remote sensing with MOCVD grown devices. And finally, this so-called Moore's law, which I hope you know is based on scaling of silicon technology from basically tens or hundreds of microns to tens of nanometers or less than tens of nanometers. So where did this start? Well, this is the inventor of MOCVD, the author of the first paper, taken in 1960s. His paper appeared in 1968, so really 50 years ago, this technology was born. Halman Asvet, who was there, is a chemist, and he was working on several problems when he started his work at Rockwell, which then was North American Aviation. Some of you may know North American Aviation is a company that historically developed the world's finest fighter planes in World War II for the American side and the Allies, the P-51 Mustang. They were also the prime contractor for all Minuteman I, II, and III missiles. And at the time, you might imagine designing a guidance system for a Minuteman missile and thinking about its trajectory and how it was going to have to travel not only long distances, but perhaps through clouds of nuclear that occurred either before it arrived or perhaps as part of a shield that opponent was going to use. So your circuits have to survive large doses of nuclear radiation, high energy particles. And silicon was a bad technology because silicon devices, as being pretty insulating, silicon being insulating, so undoped, and the radiation produces conducting silicon. So your integrated circuits die. Immediately, they stop working, system fails, and you have no idea where your missile is. So Dr. Asvet was working on silicon epitaxy and developed silicon on sapphire. Sapphire, you all know, is an oxide wide bandgap insulator. Single crystal sapphire was commercially available. And it would not become conducting, no matter how much radiation you threw at it. So if you could put silicon on sapphire, perhaps your circuits that guide your Minuteman missiles to their target would be more reliable. In the same technology development, he decided that it would be interesting to put 3,5 semiconductors on sapphire, on insulating oxides. So he developed gallium arsenide, aluminum gallium arsenide, gallium nitride, aluminum nitride, and a bunch of other things. Basically, most semiconductors composed of 3,5, 2,6, or 4,6 atoms on sapphire, on beryllium oxide, other oxides. There was no application for this initially. And many people sort of either ignored it or thought it was a waste of time because the material wasn't of very high quality. As a chemist, he didn't care. He was interested in the epitaxy process. This is a reactor I built 40 years ago at Rockwell, and it was really state-of-the-art. This is the reactor that produced the first MOCVD-grown laser diodes, the first MOCVD-grown solar cells, and had a computer control. This is a computer, if you can't recognize it. It was programmed with IBM punch cards. So yes, I know how to use IBM punch card machine. I handmade this. Every little piece of this I handmade and touched and fastened together and plumbed and wired. And the actual operating envelope is here. It looks something like this. This is an RF coil, quartz cylinder, a graphite susceptor coated with silicon carbide. This is a sapphire wafer. It's oval because this is a 100 crystalline sapphire substrate, and the boule that was used to produce this was grown on a different plane, so it was cut on angle. Instead of producing a circle, it produces an oval. So this is about a 2-inch wafer. Here's a millimeter scale and an inch scale. So this was state of the art. You couldn't buy a reactor like this. No one would sell you one. You had to make it yourself. And largely, this was the first tool that made devices that people recognize state of the art. Let's turn the clock forward to 1991, 25 years ago. What's going on in the world in 1991? Well, I'll connect this to 3.5 semiconductors later, but this slide shows you what was going on. Nothing much has changed. We got problems in the Persian Gulf. Soviet Union's a mess. Russia's a mess. But Yeltsin was first free elected leader of Russia at that time. Sadly, his selected follow-on Professor Dr. Putin, Mr. Putin, KGB agent Mr. Putin, is probably not as good a leader in some respects, but nevertheless, he is leader. South Africa changed. Tokushima blew up. The Hubble Space Telescope was launched. Hubble Space Telescope, with all those beautiful images that you're used to seeing, uses MOCVD grown sensors. So the infrared images you see from Hubble largely come from something called NIC, which is a MOCVD sensor-based tool. And here's the interesting thing for you, perhaps. This is the first web browser ever produced 25 years ago. And our GDP was 5.9 trillion, and our debt was 3.6 trillion. That same year, 1991, 25 years ago, this is what a production MOCVD reactor looks like. This is sort of state-of-the-art production tool. You can now buy a reactor made by someone to your specifications. Maybe not entirely customized, but pretty much entirely customized. So you showed them what you wanted and they built it. There's one wafer in here. This is RF coil. It looks a lot like the reactor I showed you, only it's tipped over horizontally now instead of vertically. And all the switching valves that you saw that I hand produced are now welded together in a single block. So quite compact. It's now operated under low pressure with a big vacuum pump sucking on it during growth. This is another 1991 event that changed the world. Some of you may know the Nobel Prize recently in physics was given to 3 inventors of the blue LED, supposed inventors of the blue LED. One of them was Nakamura. In February of 1991, he made the first P-type gallium nitride using magnesium and thermal annealing, post-growth annealing, in this style chamber. Single wafer, looks like mine, basically. It's got a resistance heater, a small graphite susceptor, and this was the so-called two-flow reactor. So 25 years ago, 1991, Gorbachev is out of the picture. Yeltsin's in soon. Our friend Mr. Putin's in the picture. And these reactors start being made for commercial use, and the LED, blue LED, becomes commercialized a few years later. Today, this is what you would find if you went to the store to buy a state-of-the-art commercial MOCVD reactor. This is one from Vico, made in the USA. It holds 12 150 millimeter wafers. The growth chamber is back here. This is a platter loaded with wafers, not the 150s, the smaller ones. And there are 2 or 4 growth chambers back here that this robot interfaces with. So you have 4 reactors essentially coupled together to one load interface. This, depending on your skills in bargaining would cost you about $2 million or so. Depends on features. If you do the 4-chamber one, it's probably twice that. And this is an alternative from this year. It's a different company made in Germany. Has 5 200-millimeter wafers per run. So we've gone from these reactors that had 1 2-inch wafer, which were state-of-the-art world record kinds of surface areas for 3.5 epi, to these kinds of reactors that grow basically square meters per day of epitaxial material. What do we need all that for? I mean, what do we need all that? Come on, what do we need all that stuff for? Well, a lot of it goes to LEDs now. So largely these go to LEDs. What else happened in 1991? 25 years ago, I mentioned the first World Wide Web browsers were launched. Browsers became used a lot in universities and government organizations. And in January 1993, which is a few years later, there were 50 browsers. By October, there were 500. In 1994, the first World Wide Web conference. And then here's the dot-com boom and bust around 2000. Today, from about 2000 to the present day, the underpinnings of the internet, which rely largely on photon-driven communication systems, are grown by MOCVD. And of course, based on that, we have all these nice platforms that have market values higher than a lot of countries' GDPs. So obviously, there's a lot of intellectual property in this story. But if you took away every MOCVD grown device today, you would not have a computer connected anywhere except to some maybe local area network, but not to the internet. So how has the internet changed our lives? Well, we all understand its power. This is a graphic showing how it's changed the world in terms of numbers of users, beginning with the first browsers in 1991 with 0 users, and growing, as you see here, to about 3 billion in 2014. And now in 2018, it's 4 billion. Just for your reference, the population of the Earth is 7.2 billion. So 55.5% of the known humans on this planet use the internet. An amazing number. This shows the growth of the internet versus year over this period from 2014 projected out to 2020. This projection was showing 54.6, which is already too low from the actual data from 2018, but shows you again the kind of percentage change here versus time, not likely to end anytime soon. Here's another graphic. The colors aren't so good because this is not an LED projector. Otherwise, you'd see much better color rendition here. Some old-fashioned thing called a light bulb. I don't know. It uses incandescent technology or something. I hear, but I've never seen one myself. They're kind of rare these days. So obviously, there's a lot of people in Asia. So there's a lot of this color, which is the Asian users. And this was in 2011. 6 years later, in June of 2017, that's grown to 49.7%. Obviously, the total number has gotten bigger, but the percentage in Asia has increased dramatically. And here's the saturation level of internet use. Again, penetration rates from a year ago, June 2017, and users in 2017, millions of users versus time versus location. Obviously, this is not a small thing anymore. It belongs in one of the revolutions that we talk about, the Stone Age, the Iron Age, Age of Steam, Information Age. We're beyond the Information Age now. Basically, we're in the disinformation age, where news dominates the internet, and you have bots creating phony people that tell you what you should think. And here's what that reflects is how many people interact per day with the internet. And here's a plot. This is from January this year, claiming there's 7.593 billion people, 55% in the urban environment, and internet users, social media users, unique mobile users, and active social media users. So 39% of you are on Facebook, or you were till you cancel your accounts. So obviously it's a big deal. And my point in this will be that all of this now runs on photons generated and detected by MOCVD grown devices. Here's a plot of, again, January this year, of time spent per day on the internet. It doesn't include GSU graduate students or anything like that, but you can see right here, China, USA, Russia, 6 hours and 6.5 hours per day on the internet based on, of course, the survey, which of course you say, nobody called me. I don't spend that much time on the internet, right? But that's the data. And Thailand seems to be, and Philippines seem to have a lot of spare time on their hands. I don't know what they're doing for 9 hours a day on the internet, but this could include, of course, you looking up the references for PhD dissertation and studying, the atmosphere of Mars or Jupiter or something like that. So maybe it's all productive. And here's a map of how these internet things are connected. They're connected by submarine cables. And you can see this is the global internet traffic. All of these lines are not from satellites. They're not from wires that are strung on telephone poles. They're from submarine cables that run 1.5 micron laser diodes, very sophisticated devices, and very sophisticated fibers throughout the world. Thousands of kilometers between amplifiers, actually. So indium phosphide really allows all of that infrastructure that you saw on that plot to exist, because this is the material we use for the interconnection of the Internet of Things, indium phosphide-based photonic technology, lasers, detectors, modulators, waveguides are the basis for this system. And soon, of course, we'll have fiber to the home. In Atlanta, you can't quite get that yet, but in parts of Boston, you can. The current gigabit passive optical network, or GPON, runs at 2.5 gigabits per second, which you're all going to find to be too slow, but that's what it is today. GPON, which is the terrestrial-based system, not the undersea-based system, uses dense wavelength division multiplexing and lasers of about 1.5 microns. This particular GPON uses 1.49 for downstream and 1.3 for upstream. And of TV, there's another wavelength added, 1.55. Rapidly, these are moving to 10 gigabits per second from 2.5, and data centers now, which are sources of all your Google and Amazon and Facebook traffic, are running at 100 gigabits, moving to 400 gigabits a second. This is all based on this kind of technology. This is an MOCVD reactor growing kinds of devices used for the optical internet. Here's one of the wafers being processed. And this is a cartoon of a real chip that's being used in the backbone of the internet. It's called a photonic integrated circuit. This is particularly one from a US company called Infinera that has the most sophisticated indium phosphide-based optical circuits in the known universe right now. And they're very highly integrated. So literally hundreds of lasers on a chip, hundreds of detectors, modulators, and so forth. One of the nice features about MOCVD that allows all of this technology to be developed and integrated is that you can do multi-stage epitaxy. So not just one run, but hundreds, perhaps tens of runs. This shows one of the conventional lasers that are being made. It's called a buried heterostructure because the actual active layer is right in here, and it's buried by other materials that provide the right index of refraction and doping. This shows a SEM close-up of the active layer, and this is a grating produced by lithography, upon which this P layer is regrown to provide the narrow line width required for these telecom laser diodes. And here's a SEM diagram of a cross-section through a real device, mimicking this region, as you see by these blue lines, of the multi-quantum active region and the P and N layer that provide the carriers injected into the active layer for light emission. So within this chip that you saw here, literally hundreds of lasers, modulators, and detectors are integrated based on this MOCVD indium phosphide technology. And these are the kinds of circuits that are currently in the most highly functional optical internet systems in the world, from Infinera. They're typically containing greater than 600 different optical functions with elimination of about 250 fiber connections. And they have what's called 500G capacity. So essentially, hundreds of coherent lasers on one chip. In 1991, 25 years ago, this is what you would have in your purse, I guess you would say. If you had a mobile phone, you'd have something like this prior to 1991. This is 1983 Motorola Dynatac, the first portable phone weighing almost 2 pounds. In 1989, Motorola moved to this device, the first flip phone. And it was like a brick. Didn't weigh 2 pounds, but pretty clunky. You wouldn't carry one of these today. You'd be laughed out of your dorm room. I suppose you pulled this out because you want something more svelte and more powerful. 25 years ago, 1991, this was state of the art. It launched in Europe, GSM, Group Special Mobile. These are the first GSM phones from Nokia. The so-called candy bar device cost $400. And this is Motorola's version, brick design. So it's pretty long brick, retailed for $1,000 like an iPhone today. But of course, $1,000 then was a lot more expensive than $1,000 today. So what changed? Of course, cell phones aren't really new. Recently, there's been some studies done in some remote part of Sweden, I understand, where they discovered this grave. And you can see perfectly good cell phone there from Jurassic Com. And obviously, what this leads to is of fake news. You can find a lot of this on the internet if you look for it. But in 2007, a new revolution occurred in portable telephone use based on the Apple iPhone series. What changed from those bricks and clunky candy bars to this is the power amplifiers and receivers got more powerful. And they didn't do it with silicon. Well, silicon was important, but they didn't do it with silicon. They did it with 3.5 power amplifiers and receivers. And so gallium arsenide-based power amplifiers became the choice, allowing you to make this device compact, extend its battery life, improve its functionality and power. So don't think of this device as a silicon-based device anymore, because if you took the 3.5s out of it, grown by MOCVD, it wouldn't work at all except as a small paperweight. Not even a good paperweight. Of course, now, I hope you're carrying an iPhone 10 and it recognizes you in the morning when you get up. You don't push any buttons. It says, oh, good morning, how are you? Because right up in here is an array of infrared VCSELs. Lots of VCSELs, vertical cavity, surface emitting lasers operating in the infrared. It has a digital image of your face recorded, and it recognizes you whether you're wearing a hat, a scarf, a cowboy hat, Atlanta United football hat, whatever you have on, it still recognizes you. If you put on sunglasses, it still recognizes you. I've tried, I can't fool it, except if you try to show a picture of yourself, it's flat. So it knows it's not a real person. It's looking for the three-dimensional version of your face. Spatially resolved images are stored there. You gotta like it. I mean, it's just crazy to think of what they have built in this phone. And soon you'll see these coming your way. These, of course, this is a quote real iWatch. But soon, the new versions will have micro LED displays made by MOCVD with really high intensity, really good in sunlight, and really low battery usage. So your battery in your iWatch will last a lot longer. So as I mentioned earlier, the revolution for 2007 and the iPhones and their compact, powerful designs come from power amplifiers that are based on 3.5s. This is an example of one of these. It's an InGaAs-based gallium arsenide pseudomorphic high mobility transistor, commonly called pseudomorphic high electron mobility transistor, or PHEMT, and also indium phosphide-based heterogeneous bipolar transistors, HBTs. And these are the kind of devices are providing the sensing of the Wi-Fi signals coming from the towers to your phone. You can imagine how few of nanowatts actually get to your receiver in the antenna of your phone. It's an incredibly tiny amount of power, and we can still detect it because these amplifiers are so good. Where does this lead us? Well, the mobile telephony infrastructure and power has grown dramatically. This is a plot of the mobile traffic growth from 2013 to 2018. The RF complexity, total number of frequency bands. So there are over 40 frequency bands supported. And this is the total available RF market in mobile devices. And you see this rapid increase through this recent period to about $15 billion in 2017. And this chart shows you how this whole thing has changed in terms of what's involved, what provides support for this. Shows you a different set of phone capabilities versus time, and the phones in dollars, if you will. And you can see that all of these things together amount to over $13 of value for the global LTE phone, compared to about 55 cents in the early 2G phones. So more and more of your phone depends on this 3.5 aspect of the phone, which are largely built on power amplifiers and filters. The next generation of the internet, of course, doesn't always run on fibers. It sometimes runs on satellites. This is several companies that are building incredibly large satellite networks right now. One of these companies is called OneWeb. They're putting up 900 satellites to cover the Earth. So you recall sometimes a satellite phone has a big briefcase and a big clunky headphone thing to receive. Now your iPhone will be a satellite phone, and you'll be talking to one of these 900 satellites. By the way, it's only one company. There's lots of other companies putting up similar numbers of satellites for telecom to cover the Earth from any point in the world. The satellites look like this. This is a OneWeb satellite reconstruction, if you will, artist's conception. These things are not just plates of silicon. No. They're actually plates of high-efficiency gallium arsenide solar cells grown by MOCVD. They're triple junction or quadruple, probably triple junction in the first phase. So this whole thing, besides the RF part, but the whole power system is based on 3.5 semiconductors grown by MOCVD. And as I mentioned earlier, in the iPhone case, the face recognition technology is based on infrared VCSELs, vertical cavity surface emitting lasers. These are used not only in iPhone, but for a lot of stuff. This is sort of the sensing area, device aware, optical communications, gestures, magnetic storage, 3D imaging, data centers, industrial heating, printing, and cosmetics. This is a picture of a VCSEL epi wafer, literally thousands, tens of thousands of VCSELs on a 4-inch wafer. These are very tiny lasers, but they're very efficient, and they actually can be used for industrial heating. So here's an example of a high density of VCSELs and a bunch of chips put together to form a 1.6 kilowatt industrial heating unit. full 3-inch wafer with 100% yield grown by MOCVD. So soon you'll see lasers in some strange places like heating. Who would have thought you would need a laser to heat something? But they're really efficient power usage. In principle, semiconductor laser is 100% efficient of converting electrical energy to photons, photon energy. So if you can make these in large arrays, you can make incredibly high power heaters. Speaking of solar cells, this is the first MOCVD grown solar cell in the known universe. I made it myself in 1977. This is a little cell. It's about a square centimeter that I made from one of my wafers. It uses AlGaS technology, which was the conventional state-of-the-art material system, but grown by LPE at the time, by a different technology. And very soon after, in fact, the first cell I made was nearly the same performance as the records made by alternate technology. And this is from 1979, March 14th, 1979, actually. Multiple cells from a single wafer. Those are all 1 centimeter cells, again, with state-of-the-art performance. So already we were showing that the technology of MOCVD vapor phase epitaxial growth of 3/5 could be used for very large areas relative to something else that was in use at the time. To show you where this technology is today, this is a plot from this year from the National Renewable Energy Laboratory, NREL, in the United States. It's the best solar cell efficiency in the research area for air mass 1.5. Air mass 1.5 is what you would see if you walked out today in Atlanta. Actually, if you're on the equator on a sunny day at noon, and you were just sitting on a boat or at the equator somewhere. So that's the spectrum being used for this. Starting back here in 1976, you see some silicon cells here, these little open circles. Green, the colors are all messed up on this. I guess these are not silicon cells. They must be thin film cells. Silicon cells are these guys, these squares, single crystal silicon moving through here. All of these record cells are made by MOCVD. Everything you see here and here and here is MOCVD. So all the record cells in the known universe right now are made by MOCVD. A lot of them are made by a company that Boeing bought several years ago called Spectralab. So if you went out to the space station, or if you went to Mars and looked at the rovers on Mars, Opportunity and Spirit, they'd be powered by gallium arsenide multi-junction solar cells grown by MOCVD. All of those 900 satellites you saw from the communication systems people are putting up are going to be MOCVD triple junction cells. They're going to be these kind of cells up here with 46% operational efficiency at air mass 1. So here's some examples of a space satellite with MOCVD cells, a world, if you will, surface-based array of concentrator cells grown by MOCVD. You can make large panels. These are large Fresnel lenses on the order of meters on a side, focus the light onto a small gallium arsenide cell, operate at a concentration of 1,000 suns, temperature rises to several hundred degrees centigrade, and the cell operates at that temperature and produces high efficiency electricity with 1,000 on the sidewalk by focusing the sun onto them, right? That's what we're doing. We're basically killing ants with this thing. Other applications for these cells. So if you go to Australia, every 4 years, there's a solar race with solar-powered cars. This is one of them. That one, it's powered by multi-junction cells grown by MOCVD. This solar impulse plane, the first plane in the known universe to fly entirely on solar power, was powered by MOCVD-grown gallium arsenide triple junction cells. And these guys, as I mentioned, on Mars are powered by these same kind of cells. These wings are not just there for flying, they're there for power. And those cells are all multi-junction gallium arsenide cells grown by MOCVD. Of course, the Mars rovers aren't exactly welcome on Mars. The natives have decided that they don't need this kind of strange vehicle running around on their soil. So there are some protesters there on Mars that we occasionally see. And that's what we think happened to Spirit. Spirit died a few years ago and no longer talks to us because it probably was attacked by these critters. What else can we do? Well, I mentioned sensing, and I mentioned your face being recognized by your cell phone. Obviously, other places for that kind of technology, but also other materials with smaller band gaps can be used to detect infrared and deep infrared or mid-wave infrared photons. So longer than 3 microns, 10 microns. And so you can do sensing, infrared sensing of various kinds, as shown here. Here's a plot of the spectrum that we all generally know about, the visible spectrum and nearby. And this shows where some of these MOCVD-grown devices are operating, all the way from 280 nanometers to about 1550 nanometers. These are the telecom lasers, obviously visible LEDs and lasers, Blu-ray lasers, and UVA and UVB LEDs being developed for various types of chemical processing, photon-driven plastic processing. Another place where MOCVD is used for these long wavelength detectors is in the Hubble, as I mentioned earlier. This is a schematic drawing of the Hubble. And back here, as you can see here, is something called the NICMOS box. And this is the spectral response of the detectors in the NICMOS system. Those are the ones being used to study long wavelength photons. And as you know, the long wavelength photons come from distant galaxies far away. They get stretched out because of the fact they were generated long, long ago. And the space-time is stretched. So they're now long wavelength. That sensor is based on MOCVD-grown mercury cadmium telluride. As I said here, this is an alloy, a 4,6 alloy mercury cadmium telluride grown on sapphire by MOCVD. So even long ago when Hubble was launched, they had detectors grown by MOCVD for these very specialized applications. And here's a picture that some of you will recognize because it's kind of famous, something called the Pillars of Creation, which is from the Eagle Nebula. And this whole spectrum has been colorized, but it's basically a long wavelength infrared spectrum taken by this sensor, this bi-CMOS sensor. There's another set of satellites that you don't know much about. They're spy satellites. A whole series of satellites called the KH-11 satellites were built by the US and launched. And they use the same kind of technology for a different application, of course. The space, they were looking down at Earth, detecting things that were happening. So some of you realize that during the Cold War, one of the most important things that we could do was to verify what the Soviets were doing. And you couldn't trust them. You had to verify, as President Reagan famously said. How do you verify? Well, you can't really fly airplanes over Russia very effectively anymore, at least without losing a few, as we did with the U-2 that Gary Powers flew. So you put your sensors up in space and you look down and you look at infrared signatures and you could figure out what's going on, whether a reactor is hot or vehicles are moving. So it's an important part of the Cold War. And yes, as they say now, the hot peace instead of Cold War. Someone has described what we have with Russia now as a hot peace. At any rate, they're still there looking down. To move to the nitrides, which you all know are now part of your living space in LED technology and your cell phone illumination and your TV screens and your flat panels. This is the band gap energy versus lattice constant for that system. It covers everything in the visible here, plus in the UV. So very valuable system. It's all direct band gap. The problem is that this lattice constant varies so much with the band gap change. So we have one of Mother Nature's tricks, or maybe it's a joke, right? I'll give you this system. It's all what you need. It's direct band gap. It covers the visible. It covers the UV. But it's going to be impossible to grow in some cases. You're going to have to figure it out. So we figured out how to do visible LEDs here in this InGaN system and some UV stuff, but this is still a challenge. And down here is still a challenge as well. We can't really get effectively high efficiency green light out of these materials yet, which should be possible if this were colored properly. But nevertheless, as you know, white stadium lit up with LEDs. If you go to the Mercedes-Benz Stadium and watch the Atlanta United or Falcons play, you'll see all of that LED technology in full force, lighting and big TV screens, etc. But more or less, that's the tip of the iceberg. The real part of this story comes through enhancements to what we think of as a light bulb. So they're smart bulbs. You can talk about circadian rhythm, adjusting spectrum with time. You can talk about something called millions of colors and changing some cars. You can change the color of the display panel to suit your mood. Also, something called Wi-Fi and Li-Fi. And so you can actually put an optical signal on your light bulb and send information. Something called light-fi as Wi-Fi, but light-fi, Li-Fi. So that will be the next technology for your light bulb. It won't just be an illuminator, it'll be a communicator. How does this affect our life? Well, this chart shows something about that. This shows how LED markets for 3.5 devices grown by MOCVD have changed with time and some of the future. And you can see a dramatic change here. The big part of this is the general lighting part, but a lot of specialty things as well will become important. And by the way, this chart doesn't, it's phony because it's from 2014, and it doesn't include the micro displays that you're going to be using in virtually all cell phones and iWatches and things like that soon. That'll bump these portable electronics bars up dramatically. Another place where you're going to see this play a bigger role is when we go to distributed energy and more green energy from windmills and solar power and car chargers and so forth. You're going to need more advanced 3.5 semiconductors in those spaces, and they'll be grown by MOCVD, I'm sure. And when your car starts to be smarter than you are, and you don't need to drive anymore, it'll be based a lot on sensors and electronics based on 3.5 technology as well. This shows the next generation of electronics from virtually vacuum tubes and mechanical devices to something called 2020, which shows a big silicon wafer, I guess, and how things have changed in productivity. It's calculations per second per $1,000. So you didn't get much for your money in 1900. You're using Babbage's mechanical calculator. And as time goes on, of course, your value proposition improved dramatically. And what's going to change this is the next generation of silicon-based technology. You can see this slide here has compound semiconductor silicon full-scale integration. So at some point, silicon isn't isolated from 3.5s in functional chips. It becomes part of the silicon technology. And here doing a similar plot now not in terms of dollars per $1,000, but in terms of just power of calculations and how these things have changed with different computing. Here's Babbage's analytical engine, the Colossus computer that the British used to crack the German Enigma code in World War II, the UNIVAC, the Apple II, Power Mac, and somewhere up here in your lifetime, the computer system, a single computer system will surpass the brain power of all human brains on the earth combined. So you get to tell us what that means. Is that good or bad? Right now, as you can see, somewhere around here, we're going to beat the mouse. This already happened in 2015. Human brains projected to be obsolete in 2023. So think about that. Is this really going to happen? Well, how does it happen? Does silicon get smarter? Does silicon electrons get faster? They're already at the fundamental limit of what you can do pretty much with silicon technology. And how this changes has been shown here. This is the number and length of transistors bought per dollar from silicon technology from 2002 up to 2015. And these are forecasts, so they may not be accurate. And of course, we don't have 2018. But you see what's happened is scaling silicon from 20 to 16 nanometers has lost its value proposition as far as speed goes. Of course, there's still power advantages. So when your mobile chips get smaller, the power goes down, that's good. But where does this go from here? Well, unless you do something dramatic, invent new physics, figure out a better way to move electrons, you're toast. And here's Intel's version of how this happens. Based on their movement through today from 45 nanometers in 2007 to 7 nanometers in 2017 to 2020 beyond. They don't know what's happening in 2020 and beyond. This is some cartoons of what they think might happen. Anywhere from graphene. Pretty much, as you know, graphene has been around a while. In fact, it's been around for millennia. We just didn't know about it. It's been in all the soot that was created by the Industrial Revolution, to some degree. But it took some guys with Scotch tape to figure out what it was good for. So will it ever be good for anything? Someone will have to tell me that. I don't know if it's going to be good for anything other than Nobel Prizes and a few papers. Thousands of papers, actually. But will it ever be in part of this technology development? Well, it's pretty clear right now what's happening between these two numbers. What's happening is this. This is the latest 5 nanometer node technology. I have it on good faith. One of my grad students who works for TSMC in Austin, Texas, that everybody's moving to indium gallium arsenide channels on silicon. And this is how they're doing it, integrating with SiGe. These are standard 7 nanometer technology kind of silicon germanium transistors, which are all using, if you're using Intel microprocessors. And this is the latest iteration. Of course, there's a lot of phony cartoon here. This is perhaps disinformation or fake news, but it has the basic feature that's valid, that what's going to be running your electrons in the near future is not silicon physics, it's indium gallium arsenide physics. It's 3.5 device physics. How do you make this stuff? Yeah, it's MOCVD. Every Intel plant, every TSMC plant, every Samsung plant, every plant making Apple's next processors will have a whole front end full of MOCVD reactors putting these layers down in probably the 10 nanometer to 20 nanometer thickness regime to make these devices work. So the solution for that decreasing performance feature that you saw is integration of 3.5 compound semiconductors with MOCVD grown 3.5 semiconductors on silicon CMOS. So my last slide. Some of you are familiar with a small company called Sherwin-Williams. They make paint. This is their symbol. I've relabeled their can to be MOCVD. So MOCVD is going to cover the earth. It will provide you and your at least first generation descendants with the kind of technology they need to be happy, healthy, wealthy, and productive. So thanks for your attention. Appreciate your interest. You all know these kinds of pictures, but this is our campus in Shenzhen, and this is our campus in Metz, France. If you get a chance to visit, please come by. Thank you.
Solar cells, is the incredible heat involved a byproduct of all that light coming in, or is it a necessary part of how the source of triads to get the silicon?
The heat comes from the energy you didn't use to create electron hole pairs, right? It's what makes the ant die.